Hello everyone, I'm Tom Simon, your moderator for today's SiFive webinar. I'm a semiconductor industry analyst and I write regularly for semiwiki.com, covering industry trends and new technology. I have previously worked in R&D, marketing, and sales for a number of EDA companies, including Cadence and Mentor. This webinar, titled Embedding Intelligence Everywhere with SiFive 7 Series Core IP, will have two sections. The first, presented by Jack Kang, Senior Vice President Customer Experience at SiFive, will offer a look at how embedded intelligence is becoming prevalent everywhere, from the cloud to the edge. He will also offer an overview of SiFive's embedded RISC processors and how they fit current market needs. The second section, presented by Jahur Vora, Director of Field Applications Engineering, is titled SiFive 7 Series Core IP. His presentation will discuss the features of the three members of the Core IP 7 Series E7, S7, and U7. This will include an overview of the 7 Series microarchitecture, focusing on performance, scalability, and the detailed specifications of each. At the end, we will have a brief Q&A, so if you have questions, be sure to submit them during the session. With that, let's get started. Over to you, Jack.
Thank you, Tom. So today I'd like to talk to everybody about what we call embedded intelligence everywhere. Before we begin, my name is Jack Kang. I'm SVP of Customer Experience here at SiFive. I've been with SiFive since we started about 4 years ago, and it's incredible to see the journey that RISC-V has been on and the widespread rapid adoption that it's taken in all the different markets that it's enabling. One of the most exciting markets that we see is embedded intelligence, and I'd like to spend some time today to explain to you what that is and why RISC-V is a fantastic solution for that space. So what do we mean by intelligence? Really today, when people talk about intelligence, they generally mean AI. AI to me, if you ask, put simply, is really just applying new types of algorithms to make intelligent decisions or insights from a lot of data. So as the world collects more data, we're finding new ways to deal with that data in unique ways. And the really unique thing about AI is I believe the algorithms are still changing. They're rapidly evolving. But what's clear is that more and more compute is needed. And we see this trend from the cloud to the edge, right? So whereas it started in cloud servers, a lot of AI algorithms doing training and inference, it started to move over to edge compute, having regional servers so that you don't have to go all the way back to the cloud, and now moving into edge devices. So at the devices themselves, where the data is gathered or information is captured or stored, we want to do sensing, we want to do training, we want to do inference on that data right at that spot. So we really see this AI or the intelligence where the compute is happening is migrating from the cloud all the way to the edge. And you see that by the market projections of the number of AI edge devices. You can see this huge growth from where we are now to 2025 in terms of just AI growth in all product segments. So if you look at the attach rate, and by this we mean, what percentage of these devices have some sort of AI processing capability. In 2018, there's roughly a 10% attachment. And really by 2025, it's anticipated that pretty much every device that exists will have some sort of AI capability. So this is really interesting because, where AI started, it was a very expensive computational thing. It was reserved for, big servers, big CPUs, big GPUs, big engines were the only ones that were doing this. But now, as it expands to more devices, we really see what's called this on-device embedded intelligence. So what's different about embedded intelligence versus, I guess, a traditional AI intelligence? So to me, when we talk about embedded devices, these are things that touch the real world or have real data. So think of things like sensors or flash storage. Something that's real and touches the world, real data, real sensing. These have unique requirements traditionally because you have to process this data in real time. And you're combining the capabilities of doing AI and intelligent information with the requirements of these embedded devices that have to exist in the real world. And I keep emphasizing real world because when you have a sensor out in the field or you have something out on the edge, besides the AI processing, you have to respond to its environment in a deterministic, predictable, real-time capability. So we need devices that can support the embedded use case, but that also have the computational capability to do AI. So it's really combining these two worlds where previously, if you look at what's traditionally been happening in our semiconductor space, have been served by two very different types of processing capabilities. Small microcontrollers or small embedded devices have much different types of CPUs and computational compute than the devices we would traditionally think of as handling AI. And we really see these blending together because every product in the embedded space needs AI attached. So with that, then we get into why RISC-V. And RISC-V was really designed as an ideal mechanism for domain-specific architectures. So domain-specific architecture, in this case, embedded intelligence is one example of that. It really allows you to target very specifically particular architectures in unique ways because it was designed from the ground up and it's a recent innovation. It really fits modern programming languages, modern software paradigms, and modern requirements much better than legacy ISAs, many of which were designed decades ago when the compute use case was different. And in those previous ISAs, obviously they've kept up with the times, but as time goes on and you're adding more things to it, it becomes bulkier and simply just less efficient. So RISC-V is a very simple, it's stable, it's modular. It allows you to add and remove things that you don't need. You can customize and extend it for your specific applications, making it very well suited for domain-specific architectures. All the time while doing so, maintaining and staying within the common software ecosystem with tools ranging from open source tools to third-party commercially supported products. And because the RISC-V ISA itself is open source, we see huge momentum in the number of companies that support it, the number of software, the number of folks who are using it. All of this adds up to a very robust ecosystem for an ISA that really is designed to be extended into very specific types of products. So with that, that's why we see RISC-V achieving the success that it's had in a very short period of time. So when we talk about SiFive core IP, SiFive as a company, we do offer multiple versions of commercial RISC-V cores that are silicon proven and verified for our customers to use. I'd like to talk a little bit about some of the markets where we see this embedded intelligence taking off. So the three I'm going to talk about today is consumer, storage networking, and then machine learning edge. So on the consumer side, we really see a lot of new categories of devices, AR, VR, things in the smart home, all of these things becoming more intelligent, wearables as an example, taking advantage of the sensor capabilities of these products to deliver new experiences. On the storage and networking side, this is where maybe people think of the traditional AI because they think of the cloud servers, but really within itself is a large ecosystem. So within, think of a big server, big database, big cloud server center. Within it, not just the big compute devices, but inside the storage that exists inside, the SSD controllers, the switches, the SmartNIC, the offload cards, all the various components in that space are all becoming intelligent by themselves. And then the third one, machine learning edge, I think this is, maybe some people talk about this a little bit more because it's very related to IoT, which is a big buzzword. But to me, these are all the devices out in the world, gathering data, connected to sensors, the gateways which they gathered information before sending it back up to the cloud. This is kind of the machine learning edge, and this is a clear place where intelligence is being added to all of these devices. So in the AR/VR sensor fusion area, a couple of key characteristics are really important here. You need very low power consumption because these are battery-driven devices. So you need to have the cores that are the right size and the right fit for these products. One of the unique things about SiFive design, as you see on the upper right, is we can combine multiple series together. So in these devices, often there's many different compute clusters or compute cores, each of which is doing different functions. So you might have some embedded cores who are, processing your gyro data, some embedded cores that are processing the sound data. You have a lot of different things going on. You need a lot of different cores of different types of compute. So with RISC-V, you can use the same instruction set for all of these different compute clusters, but have different size cores within them. And within each one, you can do a lot of workload-specific customizations. You can extend and you can customize the instructions within each of the particular cores. We have very easy ways to add accelerators on the outside. We have a low latency peripheral port. We have coherent accelerator, all things that let you add in your own accelerator depending on the functionality that's needed. And the real nice thing about this is because all of these cores, despite being different sizes and different compute capabilities, because they're all running the same RISC-V instruction set, we can deliver what we call coherent in-cluster combination, which means we can put the quote real-time cores with our application cores in the same coherent cluster, making it very easy to share data around. So one example of a use case for this is you can use your embedded cores to run your real-time processing, for example, the movement of the head, so processing the gyro information so that you can adjust your AR device in real time. You can put that with a much more beefier, much more powerful application core, which is running some AI algorithms, and you can share the data very easily and coherently. So this is some very nice things about the architecture and about how SiFive is implemented that make it a good solution for this space. As another example of where a lot of people are taking advantage of SiFive cores and RISC-V is in storage. So storage is another example where the coherent in-cluster combination of the application processor and real-time processors are quite unique. If you think about storage devices, whether it's spinning disk or flash media, you have a lot of very real-time requirements, right? You have to process the data right when something spins to it, or you need to go read the actual flash itself, and you have very deterministic calculations that you have to do in order to know when the data is going to show up. So that requires real-time cores, but you also want the capability of powerful application cores to run intelligent algorithms from that. Right? One of the big pushes in storage is computational storage, where rather than sending the data out to the main CPU for processing, it's much more efficient from a bandwidth standpoint, from a power standpoint, from a latency standpoint, to do the intelligence right at the storage device and only send the relevant data back up to the larger CPUs. And so having the ability to have deterministic processing and tight control here is quite important. One other interesting thing about RISC-V that lends itself very well to the storage space is it allows for taking exactly what you need because it's a modular instruction set. So for example, in RISC-V, you can go to 64-bit processing today. You can have 64-bit embedded devices, and you don't need to carry with it the floating point unit, for example. You don't need to carry with it multimedia type instructions if you're using it to process the firmware. You can pick and choose what you need because it's modular. Today, many of the existing cores that are 64-bit come with it a penalty, power and area penalty, because they were designed for other markets, not necessarily for this one. So being able to remove what you don't need, like floating point, but being able to add in specific custom instructions or other things that you do need, make it a very powerful and efficient choice for this market. We go to 5G and networking. Here, it's complex arithmetic is a key part of the compute capability, and having high bandwidth accelerator ports to enable the offload is very important. So the same type of characteristics that allow for the customizations also apply here, except here we might be using much more higher end cores. For critical real-time workloads, SiFive offers ability to have both tightly integrated memories, which is SRAMs. You can store used data that you need very often, or you need to access very deterministically as well as caches for large applications. But within the caches themselves, there's a lot of flexibility in how to lock lines and other things to enable those type of compute. So really designed with these new type of applications in mind. We'll talk a little more detail today about the cores themselves, but we think they're quite good fits for all of these markets. And as an overview for SiFive cores, this is the cores that are commercially available from SiFive. They're roughly basically divided up into 3 types: U cores, S cores, and E cores. The U cores are our application cores. So this is the ones that you would use if you wanted to run a full-featured operating system. It supports virtual memory. It has additional privilege modes, TLBs, MMUs. This lets you very quickly adopt different types of software that's written for things like Linux or other type of applications like that. We also then have 2 families of embedded cores. The S cores, these are our 64-bit embedded processors, and our E cores, which are our 32-bit embedded processors. So depending on your application, you have your choice of 32-bit or 64-bit. In all of these cases, one unique thing is you can combine the U cores, for example, with the S cores in the coherent single cluster, which gives you the best of both worlds, where you can use the S cores to control your embedded real-time application, and then you can use your U cores maybe to quickly run algorithms that have already been written for in a higher-end environment. So we'll talk more about this detail in the next few slides, and then dive deep into a particular series. So within this, we have different series which represent different size and types of compute. So the smallest and most efficient cores that we have is what we call the 2 series. Within the 2 series, we have the E2 and the S2. So the E2 is our 32-bit embedded processors, and the S2 is actually the 64-bit embedded processors. So the E2, most might be familiar with. This is the type of core that you would use in many traditional microcontroller type applications. It's very small. It has very low latency interrupts. It's configurable, but it's really intended for small control processors out in MCUs or edge devices. One unique thing that SiFive does offer is our S2. So this is a 64-bit version of the E2. So why would you need this? Some people often ask me. Well, in many devices today, the high-end compute, the main CPU is all 64-bit, and you actually have a 64-bit SoC. But there still is a need for lots of type of control processing or other types of management functions within that SoC. By using the S2, you can still have a very, very small control core, but still have this 64-bit capability, so you can have a consistent software experience. So S2 is quite an interesting choice as I would say, a companion core in larger SoCs. Then we get to a 3 and 5 series, and these are the most widely deployed RISC-V processors IPs today. There's multiple customers who have used this. It's been silicon proven multiple times by SiFive and our customers. So the E3 is our 32-bit embedded processors. The S5 is our 64-bit embedded processors, and then the U5 is the 64-bit application processors. So common within all of these is it's a very efficient performance. It kind of hits that middle of the road. It offers coherency and it offers heterogeneous multi-core, so you can combine different types of these cores together. And there's a lot of capabilities built into this for real-time capabilities. So things like even disabling branch prediction so that you have a very deterministic and predictable performance is something that's available on these cores. The newest cores that we've announced is the 7 series. So this is a higher performance core than compared to the 3 and 5 series. Johor will talk more in detail of the 7 series in the second half of this webinar. But the key takeaway here is there's an E series, E7 series, an S7 series, and a U7 series. So similar to the other cores, you have different options here between a 32-bit embedded, 64-bit embedded, and a 64-bit application core. Because they have a common feature set, they all share their real-time capabilities, and you can mix and match these cores together in your system. And the latest core that we've announced, the highest performance core, which we will not talk in much detail today, but I wanted everybody to be aware of it, is our U8 series. So this is a 64-bit application processor. This is an out-of-order core. This is the highest end performance core that we offer today. The key thing here is if you see the scalability of RISC-V Even in what we're offering today, we scale all the way from small microcontrollers like E2 all the way to pretty high performance, out of order application UA processing. So, with that, I'd just like to kind of maybe summarize a little bit what we mean by embedded intelligence. It's a whole class of applications that demand efficient performance, real-time capabilities. Because embedded devices are so broad and we see AI attached being so widespread, you need to deliver a platform that has lots of scalability. You need to have different cores that range from small to big so that you can use different cores for different applications, but leverage your software stack, leverage your ecosystem, leverage your designs in ways that couldn't have been done before. We've seen over 150 design wins that we've announced in all sorts of different markets. Some of the ones which I talked about today, we really think that these are growing areas, and it's a really important segment for us that we continue to invest in. Some examples of some public products that I can talk about in kind of the segments that we just said. Wearable AI, Huami announced a whole line of different smartwatches and fitness trackers. These use a RISC-V core inside. These are kind of AI-powered watches that can track your heartbeat and make a lot of intelligent decisions about your health. On the storage side, Fadu is a company that has announced their storage controllers using SiFive cores by taking advantage of the customization capabilities that they had. They publicly stated they reached 1/3 the power and 1/3 the area using SiFive cores compared to the alternative. And on the edge, finally, Microchip has recently announced their PolarFire SoC. This is their FPGA. Inside, they're using a heterogeneous cluster of U5 and S5 cores together. So with that, I'd like to turn the presentation over to Johor, who will talk a little bit more details about the 7 series cores today.
Okay, thank you so much, Jack. Hi, everyone. My name is Johor Vora. I'm a director of field applications engineering team here at SiFive. And I'm based in Austin. I've been with SiFive for the last 1.5 years. However, I've been in the processor industry for the last 20 years. So let me spend some time kind of giving you a quick intro to the 7 series. So the 7 series is our highest performance dual issue in order commercial availability of our RISC-V processor IP. The 7 series essentially comes in 3 different flavors. We have our 32-bit embedded 7 series core called the E7. We have a 64-bit embedded processor as well, which is an industry first as far as the 64-bit real-time core is concerned. And then we also have a Linux-capable U7 core available as well as part of our 7 series. All the 3 cores essentially have a very common feature set. They are hard real-time they have feature sets that make them hard real-time capable. And then they're highly scalable as well, and we'll see more in the next few slides. So going through some of the feature set of the 7 series in general, as you can see, I think one of the important feature set is scalability. So you can put up to 9 cores into a single coherent cluster, if you will, whereby you can combine the Unix cores with an S7 cores, thereby giving you real-time cores and application core in the same core complex with a coherent memory system. The designs and the individual cores are extensible. So we support an interface called SCI, SiFive Custom Instruction Interface. Using that interface, you can attach and add instructions to the pipeline of the CPUs. We provide a memory system that is significantly configurable. And essentially, that allows you to tailor the implementation into the SoC that you are designing these cores into. As I said, we support the L1 caches, which are local to each CPUs, as well as we have a unified level 2 cache. On top of that, for more predictable performance, we support tightly integrated memories as well. Those can be local to the cores. We also have a shared scratch pad memory that can be shared between all the cores. All these cores are 64-bit, they provide 64-bit addressability. So if you look at the U7 and the S7, they're 64-bit cores. The E7 being a 32-bit core provides you 32-bit addressability. We support mixed precision arithmetic on all the cores. The U and the S and the E cores can be configured with a single precision or a double precision floating point unit as well. In terms of the caches, they're very flexible. So the caches can be configured, can be locked for more deterministic performance. But when it comes to the L2 can essentially be configured to behave as a scratch pad memory, which can be cached in the L1 or a loosely integrated memory as well. You can also proportion the cache to the different CPUs in the core complex, thereby partitioning the cache bandwidth to any number of cores in the CPU, thereby giving you more predictable performance from the L1 and the L2 memory system for specific cores in the CPUs. Thereby, you can have real-time cores that are guaranteed to have allocated bandwidth into the L2 versus Linux cores, which can use the bandwidth as and when available. The other important feature here is the amount of integration that we provide. So when you configure all these cores, you get significant integration, thereby reducing your design integration effort, verification effort. When you configure the cores, they're available as a single verified pre-integrated core complex that not only includes the cores, but also things like multi-core debug, multi-core trace, as well as interrupt control that connects to all the different cores in the core complex. The cores do have features that improve the reliability and makes them suitable for functional safety type applications as well. We have ECC support, secondary ECC support on all the caches, as well as comprehensive error logging features on some of the cores in the design. There are features within the CPU core complex that, again, enhances the determinism of the CPUs. One of the examples there being the ability to disable the branch prediction unit, for instance, through software, if you want to make the cores more deterministic. So there is a detailed Lindley report out there on the microarchitecture of the 7 series. If you look at the 7 series, it's comparable to some of the other ARM cores out in the market. If you look at the E7, it compares fairly well with the M7, but giving you significant configurability to better suit it in the application that you're designing into. If you look at the U7 gives you significant power and area efficiency over comparable ARM core, for instance. As you can see from these numbers, the U7 gives you similar performance to the ARM core in about 1/3 the area. Let's spend some time looking at the microarchitecture of the 7 series. So looking at the E7 feature set, so the E7 basically is a 32-bit RISC-V core. It supports the compressed instruction set as well as the G extensions, which is essentially the IMAFCD V extensions. We're also adding vector capability on our 7 series, so that will support the vector instruction set as well. In terms of the pipeline, it's a dual issue in order 8-stage Harvard pipeline. And the memory system is very flexible around the CPU. So you have optional instruction cache, as well as an optional data cache. We also give you the option to include instruction and data TIMs. So for instance, on the data side, you can have a data cache or a data TIM. The 7 series also has what we call our FIO port. So the FIO port allows you to have a low latency interface into scratchpad memory onto the buses or a register interface. These cores are multi-core capable with coherency and optional L2. So if you need an L2, we have a unified L2 that you can attach in the core complex. The core comes with a CLIC, which is our core local interrupt controller for fast, preemptible, low latency interrupts. And then on top of that, you also have the PLIC, which is a global interrupt distributor. So in a multi-core configuration, typically you would have a PLIC that would route interrupt from the various sources in your design to the respective cores in the core complex. The 7 series microarchitecture is designed to provide higher throughput and efficiency versus some of the comparable options like an M7, for instance. You get about 2.3 dry stone MIPS per megahertz, about 4.9 core marks per megahertz. Okay, so looking at the 7 series, the S7 series, essentially it's the same microarchitecture as the E7, but the 7 series brings in 64-bit capabilities. So it has the RV64 ISA. It does support the same optional RISC-V extensions that includes the M extension for multiply, the FND for single and double precision floating point. It does include the compressed instruction set as well as the vector instruction set. Again, as I said, it's the same microarchitecture, so it's a dual issue in-order 8-stage Harvard pipeline. The memory systems is also very, very similar to the E7 and the U7 cores. So again, you have the optional instruction cache as well as an instruction TIM. You can either have a data cache or a data TIM on the data side, and then you do have an interface into low latency interface into the SoC peripherals through FIO port or to attach large SRAMs. The S7 is also, of course, multi-core capable and does have a coherent L1 across multi-cores with the option to integrate a unified level L2. The S7 supports the same interrupt controllers as well. So for instance, if you're using a single S7 in a design, you would typically use the core local interrupt controller. In a multi-core configuration, typically you would use the platform level interrupt controller. The S7 is comparable to something like an ARM Cortex R8. In terms of performance, you get about 2.5 DMIPS per megahertz, 4.9 core marks per megahertz. So looking at the U7 brings in the supervisor mode. So now you have RV64 GCV with 3 modes. You have 3 privilege modes. So you have the user mode, the machine mode, and the supervisor mode. The supervisor mode supports the SV39 MMU. So essentially you have 39 bits of virtual addresses. Again, from a microarchitecture standpoint, given it's a 7 series core, very similar to the S7 and the E7, dual issue in order Harvard pipeline. The unique feature that the 7 series provides is the ability to combine heterogeneous in-cluster combinations of the various S7 cores. So for instance, you can combine an S7 with the U7, thereby within the same core complex with a shared coherent L1 and an L2, providing a performant memory system to the heterogeneous core, thereby reducing bandwidth and traffic onto the buses, for instance, in a multi-core configuration. The L2 does come with the ability to lock the caches, so you can allocate it into the L2 purvey. The L2 does have a mode whereby it can behave as a loosely integrated memory, so it appears as a memory map device in your memory map. It also has a mode whereby you can configure it as a scratchpad memory, essentially, whereby when configured as in scratchpad mode, it behaves as a cached loosely integrated memory that's cached. All the memories in the cores are support ECC, so we support secondary ECC on all the L1 and L2 memories, including the caches and the TIMs. The 7 series cores also support the PMP, the physical memory protection, and the MMU in the U7 case for virtual to physical memory address translation. You do have the ability to programmatically clear and disable dynamic branch prediction in the U7 core, thereby making it a little bit more deterministic if you were using the U7 for real-time application. Again, the U7 would compare fairly well with something like a Cortex A55 with higher efficiency and throughput. So from a dry stone standpoint, you get about 2.5 dry stone MIPS per megahertz and about 4.9 core marks per megahertz. So diving deeper into the microarchitecture of the pipeline. So the 7 series has 8-stage pipeline. It's a dual issue pipeline with multiple execution units for superscalar execution. Looking at the issue slot, we have 2 issue slots. The first issue slot performs memory operations and integer operations. And then you have the second issue slot that does multiply divide operations that also does branch resolution and floating point operations as well. Both the issue slots include ALUs in the stage 5 that handle most of the arithmetic operations. Branch resolution typically can use the output of the ALUs immediately, resulting in a 5-cycle branch mispredict penalty. If an ALU instruction requires output of a pending load, for instance, it proceeds to stage 7, which contains a second set of ALUs. Thereby, this late ALUs enables a zero-cycle load-to-use latency, meaning that a dependent ALU instruction can issue immediately after the instruction that loads data. Now, looking at the fetch stage, the fetch stages have 2 stages. Again, the second stage was added in the 7 series to support larger caches and scratch-pad memories. If you look at the decode stage, the second decode stage essentially handles superscalar dispatch and leaves more headroom for optimization that combine multiple instructions in each issue slot. So if you look at the memory system in the level 1 memory system in the S7 and the E7, as I said, the biggest benefit here would be the configurability that we provide around the memory system. So you can configure the instruction cache. Further within the instruction cache, you can configure the size of the instruction cache, the associativity of the instruction cache, the number of cache trays. In some cases, you can also configure the block size of the line, cache line as well. On the data side, you have the data cache or the data TIM. So we can support both. We can support one or the other. And then you have data local store, which is there to support larger memories if you wanted to attach them closer to the core. On the instruction TIM side, we have an optional iTIM that is also configurable. So you can include it as part of your configuration, or you can remove it. There is also the option for an FIO port. So if you wanted a low latency interface to peripherals or an accelerator, for instance, the FIO port can be used to attach accelerators fairly closely to the core with lower latencies. Let's look at some of the improvements that we made from the 3 and the 5 series in the E and the S7 series. So from a pipeline standpoint, it's still an in-order pipeline. We increased the number of stages in the pipeline as we went to the 7 series. In terms of the ISAV, we still support RV32 and RV64 with all the optional standard RISC-V extensions supported as well. Floating point, again, nothing changed there. Pretty much we support the single precision and the double precision floating point unit on both the 3 and the 5 and the 7 series. The issue weight was increased, so it's a dual issue core, giving about 50 to 60% higher performance improvements compared to the 3 and the 5 series. And then on the instruction side, we added the optional instruction cache as well as the optional instruction TIM. And then on the data side, we support the data cache or the data TIM in addition to the FIO port that's available for attaching larger SRAMs or closely coupling peripherals together. Given the improvements in the microarchitecture with the addition of the second stage ALU in the pipeline, we improved the load to use delay from 1 cycle to 0 in the 7 series. And then, of course, the addition of the FIO interface, you can now have access to fast SRAMs with 2 cycle additional latency to SRAM latencies for accessing those SRAMs. One of the other technology that we make available with our 7 series cores is SiFive Inside. So our debug and trace solution is branded as SiFive Inside. We support multi-core debug across all the cores. We also support multi-core trace. So you can configure the trace subsystem around the core, whereby you can essentially have and choose a trace macrocell for each individual core in the core complex. We support multiple different options in terms of how you sync those traces. So you can sync those traces to an on-chip SRAM. You can sync those traces off-chip via pins, or you can port it. You can trace those trace messages and put them onto, for instance, an EMBA bus or a tiling interface. We also support secure debug as well. So we added an authentication module in our debug interface that allows to deploy a public key cryptography-based debug authentication protocol, thereby provisioning secure debug into our debug and trace offering. As I said, one of the benefits here is that the debug and trace IP is just a configuration configuration knob that you select. Thereby, it reduces the effort in terms of verification and integration when you add debug and trace to the SiFive cores. The other technology we provide around our cores is SiFive Shield. So that is our brand for security solutions. So SiFive Shield is scalable, it's efficient, it's easy to adopt, very modular, and it's a complete security solution for any RISC-V SoC that you may put together. So for instance, we enable things like root of trust implementations. We provide hardware crypto engines that enable implementation of root of trust. From a threat prevention standpoint, we developed a technology called WorldGuard that essentially allows you to propagate security attributes into the memory system all the way onto the SoC caches and the different interfaces. We've also implemented countermeasures and things like fault mitigations, DPM mitigations as part of our threat prevention technology as part of SiFive Shield. The cores have been designed to be resistant to side channel attacks, things like cache leakage attacks. On top of that, you also have the RISC-V PMP, the Physical Memory Protection Unit, as well as the PMA that enables to partition your memory space into secure zones for secure execution of code. On the crypto side, we have crypto engines that support RSA, ECDSA for key management, SHA for authentication, AES, random number generators, and all that. So essentially, again, the value proposition here is you can just configure these IP blocks, and we provide them pre-integrated as part of our CPUs. We are also investing a lot in terms of the software on the security side of things. So we're making the open source, we're making our secure boot open source reference implementation. So essentially, you can take that as a starting point and leverage our crypto engines to build a secure boot. We're also open sourcing our crypto libraries as well that leverage the crypto accelerators that are part of the SiFive Shield offering. We're also adding support for secure boot in Linux or FreeRTOS. We're also providing a lot of examples in terms of secure boot as part of a Freedom SDK, and that we're implementing APIs to call the crypto libraries as part of our Freedom Metal offering as well, as part of our toolchain. So looking at a bit more detail into a typical SoC architecture or system architecture using a U74MC configuration. So the U74MC essentially allows you to have one or many Linux-capable cores or U7 cores in combination with, for instance, an S7 core. And you can configure these cores and the memory system around these cores independently. So for instance, in this case, you have a U7 core that is configured with an instruction cache, with parity, and then you have a data cache with ECC. If you look at the S7 core here has instruction cache with parity, and it also has an instruction TIM with ECC. And on top of that, you have a data cache which supports ECC. Both the S7 cores here have been configured with an FIO port, which allows you to attach a local accelerator closer to the core as a low latency interface, as well as you can attach a local SRAM to that particular core that is available as well. All the cores are integrated through the SiFive main core complex. And the main core complex essentially can be configured to ease and provide a lot of flexibility in terms of how you integrate this core complex into your SoC. So for instance, you can configure the front port. The front port is an IO coherent port that allows external accelerators to coherently access the L1 or be coherent with the L1. On top of that, you have a system port. So that is for your high bandwidth accelerators in your design. And then you have a memory port, which maps all the cached addresses in your design into your memory map to things like a DRAM or a cacheable coherent SRAM sitting on the memory port. The peripheral port supports hardware atomics. So if you need support for hardware atomics on your peripherals or memories, you can essentially integrate them behind the peripheral port. And then again, as I said, this also gives you on top of this, you can essentially add multi-core debug, multi-core trace, and crypto accelerators to give you a much highly integrated subsystem with the 7 series. Besides the configured core, we also provide standard cores. So standard cores are pre-configured cores that serve as a reference point, but we also essentially silicon-proof them as well. So there are benchmark in terms of what's possible. So customers have the freedom to choose a standard core or design a pre-configured core using SiFive Core Designer. The standard cores are available as FPGA bit files for evaluations. So from a standard core perspective, if you look at the 7 series of the E7, you have the E76 as a standard core, and then you have a multi-core version of the E76, which is the E76MC. On the S7, you have the S76 and the S76MC, which is a multi-core. And then on the U74, you have a single core U74, and then you have the U74MC, which is a heterogeneous combination of a quad U7 core and a single S7 core. The configurability of the cores is enabled through a web interface called SiFive Core Designer. So a customer typically comes in via SiFive Core Designer, and through this interface, you can configure the modes and the ISA within the core. So you can configure the privilege modes that are available. You can configure the optional standard extensions, so things like the multiply extensions, things like the floating point extension, atomics extension as well. And if you choose to add custom instructions, you can essentially leverage the SKY interface, and you can configure that as well through this interface. Again, through this interface, you can configure the memory system, so it allows you to configure the size of the caches, the types of the caches, the associativity of the caches, whether you want to have TIMs or not. All those options are configurable to SiFive Core Designer. You can configure the number of ports in terms of your SoC integration options, so those are configurable. You can configure security, so you can configure whether you want to have the PMP on one or many cores. That's also a knob that you can essentially click on SiFive Core Designer. We make the debug highly configurable as well. So for instance, on the debug, from a debug standpoint, you can choose up to 16 hardware breakpoint units within the cores, for instance. So that is also configurable. You can configure interfaces like the debug DMA that allows the debugger to pick and proc memory independently of the core. You can configure all the trace options, whether you want to have multi-core trace, the type of syncs that you want. Those are all configurable through SiFive Core Designer. Interrupts as well, so you can configure the platform level interrupt controller, the number of bits you want to have for setting the priority levels. Those are all configurable options. And then some of the options on power management, the options on the branch prediction unit, those are also configurable. So you can optimize the branch prediction unit for performance or area. Those are all knobs you can turn through SiFive Core Designer. Once you configure the core, typically what we do is we provide you RTL within 24 hours. This RTL is configured to match the configurations that you have. You get a test bench with the RTL, and you get all the supporting collateral that you need with the CPUs. So these would be all the documentation that matches the memory maps and the ports that you've configured. Not only that, you also get a board support package that is targeting with the device tree that targets FPGA bit files that we provide, but also simulation environments. So that is all configured. You get a full Freedom SDK. The SDK comes with a lot of examples that allow you to get started fairly quickly in a simulation environment as well as in an FPGA environment. So to summarize the talk, the S7 essentially gives you a lot of choices and a lot of configurability. Thereby, it allows you to trade efficiency with performance and power and area, and also tune the CPU for the SoC you're targeting. The configurable options and the number of cores enable a very scalable implementation. So in terms of the CPUs you can integrate into the processor. From a feature set standpoint as well, we provide a compelling feature set that allows you to configure a processor that is best fit for purpose. Okay, so that concludes my presentation. I'm going to now pass on the ball to Tom for Q&A.
All right. Thank you very much, Johor and Jack, for your great presentations. We have a few questions. The first question here is for Jack. RISC-V is relatively new compared to other existing ISAs. How is the ecosystem shaping up to help adoption?
Thanks, Tom. That's a great question. Actually, if we look at the RISC-V ecosystem, one of the things that surprised me most positively is the speed at which it's grown. It's evolved at an extremely rapid pace. If you look at all the software that's been enabled for RISC-V, it really is quite incredible. So things, for example, the Linux kernel has been mainlined for years now, and we see more and more distributions and more packages being ported to RISC-V to pretty much the point right now where whatever package you want is already available for RISC-V. We see things like Amazon FreeRTOS last year announced official support for RISC-V. We have hardware that's officially qualified as RISC-V IoT devices. All these things are driving widespread adoption in a variety of the markets. In addition to kind of open source type software, we also see commercial support for this. So things like commercial operating systems like ThreadX support RISC-V, as well as all the major tool vendors for embedded programming and embedded development, as well as compilers are all supporting RISC-V. So today, if you really look at it, whatever software package you're used to or you're using for those applications, you'll see that the RISC-V software ecosystem is right there on par with it. And I think one of the really hidden things in the ecosystem that I think not everybody fully understands or comprehends is that about 3 years ago, the universities, at least in the United States, have started switching all of their course material to RISC-V, which means in a few short years, we're going to see all the new graduates come out of university fully knowing RISC-V, being involved in the ecosystem for multiple years and understanding what and how to use it to the fullest. So this is really where not just an ecosystem of software and products, but an ecosystem of engineers and skill set is really coming into the market. So really from a RISC-V standpoint, I really view it as a key skill for engineers and companies to adopt because it is the trend that's coming from the universities as well as from an open source ecosystem and commercial players.
Okay, thanks, Jack. Here's a question for Johor. Does SiFive Core IP support custom ISA extensions?
Thanks, Tom. Yeah, we do have customers occasionally who come and ask for how do I add custom instruction to SiFive cores. We do support that through an interface called SiFive Custom Instruction Interface. So it's an interface called Sky. As I went through the slides, and as you go through SiFive Core Designer, essentially there is a tick box that you tick that generates this interface. So through this interface, we support customers custom instructions. And essentially today, the interface supports customers adding a single cycle instruction or a 2-cycle instruction. And then we provide guidelines in terms of getting it supported in the tool chain. So for instance, today the support is predominantly available through inline assembly and compiler intrinsics. We do provide an example code in terms of how the interface works. Essentially, we provide a Verilog shell and a wrapper that makes it easy for customers to essentially do this and implement custom instructions around the core.
All right, here's another question for Johor. SiFive Core Series supports heterogeneous core complexes. Is this the same as ARM Big Little?
Yeah, sure. Yeah. So I mean, if you look at the Big Little versus heterogeneous cores, I think Big Little is trying to solve a different problem compared to heterogeneous support for heterogeneous core in the core complex. We see a lot of applications where customers are essentially running control code or application code, for instance, in IoT applications, where customer may implement sensor fusion, for instance, and may want a real-time core, but they may be running Linux on an application core. So heterogeneous core complex essentially enables that very easily through a memory system which is highly performant, lower latency. So certainly it's trying to solve a different problem than what Big Little is.
All right, thanks. Here's a question for Jack. The question is, thanks for the presentation. From an application perspective, how would I get started on RISC-V?
Yeah, there's many different ways depending on if you're kind of more hardware focused or software focused. If you'd like to play with actual silicon, SiFive offers a couple of development boards. So we have a HiFive 1, it's part of our Freedom Everywhere. This is a embedded class MCU type board for embedded applications. If you want to work on Linux type applications, we have a different board called the HiFive Unleashed that has our U5 series cores on them. So these are both hardware boards that you can get if you wanted to play with and write software for. Or you can also go to our website and you can download for free FPGA bit streams of the different types of cores that Johor and I covered today. And a lot of the bit streams fit onto a very low cost, talk about $150 FPGA board, which you can just buy. The instructions are on our website, and you can download FPGA bit streams for that. If you're more software focused, there's also QEMU simulators, as well as our own tools called Freedom Studios. So you can download Freedom Studio also from our website. It's an integrated IDE development environment, and you can connect that to like a QEMU simulator if you want to get going writing software for it. There's also plenty of third-party tool vendors that also support RISC-V. So I think there's a wide variety of options. So I encourage you to go to the SiFive website, and we also have a forum that's set up. So if you're playing around with these different boards and have any questions, you can also ask on the forums. And there's a community plus SiFive folks who can help you out answering any questions to make sure you get started.
Okay, and here's our last question for Jack. Outside of the processor IP, what does SiFive offer in this space? Yeah,
so I know today's webinar was focused a bit heavy on RISC-V and our CPU IP, but at SiFive, our goal, our mission is to really accelerate chip design and enable idea to silicon. We really want to provide companies and startups, think two people in a garage, the ability to access custom silicon. So besides RISC-V IP, we have a wide variety of other peripheral IPs, memory controllers, interface IPs, as well as partnerships with other IP vendors, which we can bring into your system. And we also offer full custom SoC and ASIC capabilities if needed, where we can actually help build and fabricate your chip all the way to supplying the silicon for your design. So if you're interested in any of those things, please reach out to SiFive. We'll be happy to discuss those options with you.
Okay, I'd like to thank everyone for joining us for the webinar, and I'd like to thank our presenters. I'd also like to tell everyone to keep an eye out for the next SiFive webinar on April 30th, and the topic is Rapid Embedded Prototyping with SiFive Software, and that will be moderated by Bernard Murphy. Thank you.